All right, let's so let's see if, and like I said, I will check your homework tomorrow. Oh yeah, but not for junior. Okay. Eventually there will be a day of directing. I'll check this book homework. I don't want to check it yet, maybe because maybe there's certain things you struggled with, or maybe it was easy. I don't know. What was you guys find it? I mean, I didn't get to say everything I wanted to say on Friday, so I was like, or Thursday. So I was like worried about my children who went home and did their homework. But I mean, technically we did give you like what you needed, but there are some nuances that I wanted to discuss and intricacies of the examples that we'll look at today when we finish off these notes. So then maybe you'll be more prepared, and I will check eventually the book homework and the worksheet I'm going to pass to you tonight as well. All right. So any other words of blessing over our lesson today? Anyone else want to say anything? Okay. All right. So let's continue where we left off, which was on this slide right here. Sid pointed out to me that I didn't actually have to find a displacement, but I did it because that's just kind of student I am, man. I just wanted to. Okay. No, we're actually supposed to find the position, which we did, right? And the distance. All right. So the distance is, and this is supposed to be sine here. I just did this on my calculator here. That's a sine. We got the components down here. Right, this here, the component in the x direction and the component in the y direction of the velocity of the particle, so this actually amounts to arc length, doesn't it? Right, it's also equivalent to asking what is the arc length of this curve from the parameter value t equals 0 to the parameter value t equals 4. If you want to like strip this of all of its real world, velocity, and you want to strip it of its real world context. That's all we're doing. So did anyone do that? I'm curious to see what you get. Whether you got what I got here. I don't know if anyone finished this example or not. I'm getting 15.433 approximately. I don't know. Someone check me out on that, but I might have. I think I typed it right. Make sure your calculator's in radian mode. Right. So if this was in meters and we're measuring time, our parameter time in seconds, then this would be measured in meters, right? In the end, the distance would be all these would be measured in meters. There are no units on these examples, though, so whatever. So anything you want to say about that? We talked about the difference between the position, displacement, and distance as being different things, and I think that's an important thing to get. Here, wait, gotcha. Oh, and then so I like highlighting the difference between these three things because I think these are the three things that get confused. But you're right. At any given time, we can compute this unit vector in the direction of motion, which is the velocity vector, just divided by its magnitude at that moment, right?
So on the moment, you're like
I think that's what they're asking for, is that unit vector in the direction of velocity. Yeah, good question. Okay, so let's keep going here. I don't know if anyone tried these. You have them, but maybe I see most of them they're blank. That's good. So maybe there'll be still some mystery and some intrigue, as we look at some of these other examples. Okay, let's make sure we have it clear in our minds because I keep messing up. Actually, make sure I see what the question is asking here before we solve it. Suppose a particle moves along a smooth curve with this velocity vector. Boom, boom. Okay. At t equals 0, the particle is at the point 1,5. That sounds suspiciously like an initial condition to me, doesn't it? Okay. So this is actually, even though we don't say it here, this is an initial value problem in the context of vector calculus. All right. So that's what we're really doing here. It's an initial value problem. All right. So determine the path the particle travels in 4 seconds, going from 1,5 to 921. All right. So I don't know that that's going to be very important for us, some of those other pieces of information, but we'll see. Here. What are we trying to find? We're trying to find the path of the particle travels. So by that we mean the position. Really, that's what this is asking for. We would like to know what the position vector is. We've been calling that r of t. Right? That's the question. So what is that function? Right? That's really what we'd like is the function r of t. We have b of t, so I think it's natural to want to integrate, right? Hopefully you have that instinct. So that's good. We should integrate. Absolutely. Let's do it. except you know that when we integrate, we get a constant when we integrate each of these things. Right? There are a couple ways you can think about it. At t equals 0, so are you okay if we just write this down all at once? Let's try it. The position that we were at time 0 was 1. The x-coordinate was 1. Plus, how far did we go on the interval 0 to t? Here, let me actually use s's in here. We're using dummy variables here. Comma, same thing, except with 5 here. The y-coordinate is 5 plus whatever y changed, however y changed, right? All right, and there it is. That's the answer, right? Now we can do a little better than that, right? We can actually say what these are, right? We can actually do the integration. But we actually have written down here the answer already. So I'm going to take the antiderivative of this thing, see if I can do it. Be 1/2 s squared minus minus 3. I guess we still want that 3 there. Sine. I'm trying to do this in my head here. Pi s. Right? Sine. So I've made it so this is kind of a definite interval, right? So on the interval 0 to t. So no c is necessary, but you're welcome to have one. It'll cancel out. And then over here, what do we have? S squared minus, plus cosine pi s. Let's just take derivatives and make sure that actually works, okay? Derivative of this is 2s minus pi sine pi s. Okay, so I like that one. And over here, I'm just going to check that one too mentally here. That's s minus 3 cosine pi s, then times pi. Yeah, okay, so I think I'm okay on those. And then we can say what each of those is. We get 1 plus 1/2 t squared minus 3 sine pi t. And if you plug 0 into that, minus whatever we put 0 into that, it's 0, isn't it? That whole thing is 0 if we plug 0 in. So I think I'm done there. This one will be a little more interesting, right? Over here we get 5 plus t squared plus cosine pi t minus what happens when we plug 0 into that, which is nothing here, but then here we get cosine of 0 is 1. All right, so that's a little bit better. Oh, minus 1, thank you, because we're doing minus. There we go. So, so if we want to write that last piece a little more cleanly, I don't know how you want to write this, but the first piece is pretty clean already. I don't know how you want to write it. But. And the second piece, we can combine the constants at least. Okay, now, I've conceptualized this in a way that I think is useful, but there are other ways to think about this problem and get the right answer. By the way, if we want to verify, let's just verify. If we plug in 4, do we actually get 921? And we don't actually need this information, is the point. Does it work? I'll check the y coordinate, you check the x coordinate. If I plug in 4, 16 plus cosine of 4 pi is still 1. Plus 4, 5, 16 is 21. Okay, so I'm getting 21. Did everyone check the x coordinate is 9? Okay, so that's a helpful confirmation. But actually, this is all superfluous information, right? Okay. It's good to know when you see it. Yeah, it's all superfluous. Yeah. Do I need that in the question? Actually, I don't. So this is. So is this? Do you understand what I did here? It's actually nothing. It's really just calculus, right? It's not. It's not like any specific thing to the context we're working with positions and velocities. This is always how this works, right? When you want to get to solve an initial value problem, right? Just to be clear, I want to make sure you're hearing me on this because I think some people are like, this looks like voodoo to me. How do I get a blank screen here? I feel like there's a way to do that. There it is. Wow, that's white as can be. Okay. If you're ever given a function f prime of x, right, equals some function, right, and you're given some initial condition, this is called initial value problem, right? You're given that f of 3 equals 7, right? I just want to make sure you're clear on this. This is like an old idea, and it doesn't necessarily just apply to positions and velocities and stuff like that, right? How do you find f? That would be our big question. This is an initial value problem, like in the most generic sense, right? How do we do that? Isn't f of 3 plus the integral from 3 to x of f prime of x dx, except we can't use x's, we have to use another dummy variable again, okay? What's your favorite letter? You like s? We were using s, so that's fine. Sometimes now we could actually use t here if we like. But this is it. That's the solution to that initial value problem. Is that clear? I want to make sure that's clear in your mind. The other way I think that sometimes we conceptualize it is we say, well, let's take the antiderivative of this, f prime, and then we'll get something, plus c, right? I think that's the way you guys like, just doing the general antiderivative. And then we plug in 3 for x and 7 for y, and we find what c is. And then we go back and put c back in, right? But I think this is also, that's completely and totally right. That will work on the example we were just doing as well. Cool. Yeah, so feel free to do it however you like, right? Take the antiderivative with a plus c at the end, and you'll get the same thing, plug in the initial conditions, and find what c is. But I like this conceptualization too. This would be, I guess, just 7 here, right? If I'm telling you that. And the reason I like this conceptualization is because I think a lot of you don't see it. There was a quiz a while ago, was this, I'm trying to think when we did this, that we asked you.
Quiz.
Huh?
Sorry. Are you talking about the quiz?
No, this was earlier last semester. I think it was, maybe it was the first test of this semester when we were doing initial value problems and stuff like that, right? And we asked you something like about a particle moving, and we had given you in the problem the position of the particle at time 1 or something was like 21, and then we told you in the question that the time that the value of the following integral 1 to 7 or something of v of t dt was like 54. And then we asked you in the last problem, and up in the problem we gave you the velocity function. We gave you the velocity function. And then we told you with this initial condition. So that is in fact the same situation up here, right? Giving you a derivative and giving you an initial value for the position, right? That's what we did. And then a lot of people did the following, right? They integrated the velocity function in order to solve the question. The last question said something like, what is the position at 7, right? What is the position after 7 seconds? And a lot of people did the following. They labored to find the actual x of t function. Well, we need x of t for this, don't we? We must have it. No. Why? Because, I hope you see it. Do you see it? What did this just tell us? X of 7 is equal to x of 1 plus the change from 1 to 7. Right? So what is, I made these numbers up, but what is the position at x equals 7? Do we need x? You think, oh, well, we need x of t. Because we need to plug 7 into it. No, we don't. No, we don't. Right? It's just 21 plus 54. Right? So I don't know what the numbers were exactly on the quiz, but does that ring a bell? Everyone, some people actually landed that correctly, but a lot of people didn't see this, and it's an important concept, I think. Okay. Okay. How do I go back? I don't know. Unweight screen? Oh, there we go. Okay. There's the picture of that motion, by the way. I've covered it up now. But feel free to plot this on your calculator in x1 and y1 of t on your calculator, and you'll get that picture. Yay, it's some swooping thing. Cool. Okay. Moving on to another example. Here we go. Nothing with cosines and sines in it. We've got some nice polynomial components to our velocity. And by the way, to our position. By the way, are you okay with the I and j formulation of how we're writing this? It's just to throw that at you, right? It's really the same. If you prefer, you can right away rewrite it as 2t cubed minus 3t squared, comma, instead if you like this kind of way of writing it. They mean the same thing, okay, just to be clear. So I hope you understand both ways of thinking about it. Write the equation of the tangent and normal line when t equals -1. Well, boy, things escalated quickly. We need to have a derivative here, don't we? How do we find dy dx? You remember? This has been a while since Thursday, or Wednesday when we talked about this stuff. Dy dx is, yeah, so we got 3t squared minus 12 over let's do it in order. 6t squared minus 6t, sure I did that right. It's 3t squared minus 12 over 6t squared minus 6t, okay. And t is -1, so for evaluating this when t is -1, this will be like our m value, our slope, right? So everyone plug that in. I'll do it too, and we can compare our answers. Let's see, -1, so 3 minus 12 is -9. And 6 plus 6 is 12. Can someone check me on that? Yeah. Okay. Yeah, I did that right. Okay, good. What else do we need? We need the point as well. If we plug in -1 into our position function, so we got the slope and we need the point at which the tangency occurs. So we get -2 minus 3 is -5, I think. And -1 plus 12 is 11. Again, someone confirm everything that I've written up here. You get the idea at least. Plug in, find the slope and find the point. That's what we've just done. And then find the equation of the tangent line is the first thing we'll do. And that would be, if we're looking at just doing it in Cartesian coordinates, it'll be y equals the y coordinate plus the slope times x minus the x coordinate. That's the slope, that's the tangent line. I kind of rushed through the end of that because I think that's stuff you thought about. It's also the first order approximation, isn't it? It's also the linearization. It's also, right, we have all these words for it. These are kind of fun. We could find the, if you wanted, someone could ask you for the quadratic approximation to this, right? What would you need? And just because we're coming off of a series unit, I thought it would be fun. How would you find the quadratic approximation? Well, it would be 11 minus, it would be 11 plus the first derivative times x plus 5, but then we'd need one more thing here, and we would have to find the second derivative too, right? So that would be okay. Second derivative divided by 2 factorial times x, again, then times x plus 5. X plus 5 squared, excuse me, yeah. And then the normal, just because we haven't done it in a while, just for fun, is y equals 11 plus 4/3 times x plus 5. If we haven't said it recently, isn't point slope the best thing ever, right? I mean, really, it's killing it, man. I mean, it's much better than what you used to do, you know? We love point slope. You want to simplify that? Don't even bother, man. It's great this way. We love it. Okay. All right, we're still on the same problem here. Moving on. Find the coordinates of each point on the path where the horizontal component of the velocity is 0. Okay, so this is a new, we're in the context of velocity, but we did this on the first day when we were doing 10.1 parametric equation stuff, right? So find where, what are we looking for? Where horizontal component is 0? What's that?
Hi, your pizza for the transportation thing is coming today.
Are you guys hungry? Yeah. It'll be here at lunch.
Like the end of the
Like right at the end.
Yeah.
Okay.
It's okay, I
Deal.
saw that.
Sounds good to me. I don't know about you guys. Hopefully that's okay with you guys. Are you guys ready to eat pizza? For people who aren't here.
It should have been tomorrow.
Isn't Ratchet so sad that he's not here? Are you guys okay? Sid, do you have a question? Sorry, hey guys. We want to refocus. I know pizza is exciting. Sid, go ahead. Sorry.
So for B, we're looking for dx equals 0.
Hey guys, yes. Did everyone here said, yeah, we're looking for where dx dt is 0. Where?
On B, right?
Where dx dt is.
No, where do you
It's horizontal. We're looking for horizontal tangent lines. So we want to think of, I mean, maybe it's clear to think about dy dx. What does dy dx need to be for horizontal tangents to happen? Dy dx has to be 0, doesn't it? Right? Vertical tangents would be where dy dx is undefined, and that corresponds to which derivative being 0. Corresponds to dy dt being 0, right? It's like when dy, we can also think of it though as maybe being a local max on for y, right? Okay, that's a little hard to think about in 2 dimensions, right? But yeah, we want to set dy dt, that numerator from dy dx, if you want to think about that way, equal to 0. So we've done this. We have. It's good to refresh your memory here. So what was dy dt? That's, well, I can redo it here. It's 3t squared minus 12. We're setting that equal to 0 and solving. What do we get? T squared is 4. So I'm getting plus or minus 2. Is that what you're getting?
But we have to find the coordinates.
Find the coordinates. So r of negative 2 is something. I don't know, plug it in. And r of 2 is something. I don't know, plug it in. Negative 16 minus 12. Negative 16 minus 12. Is that right? The negative 28?
Yeah.
Yeah.
So I actually already explained this.
Okay, go ahead.
How is the horizontal component 0? Why do you get the y over the x over
So we explained it just now in 2 ways. You could think of, so remember dy, let's maybe return to something from last semester that you remember. Dy dx, if we're looking for a horizontal asymptote, forget parametric curves. For any curve from unit 2 or whatever, whenever we talk about this. What are we looking for? We're looking for dy dx to be 0, right? We also just said that dy dx is, we wrote down dy dx on the previous problem. Oh, yeah, exactly. So how does dy dx come out to be 0 if we have some rational thing? That can only happen if dy dt is 0, right? All right, so that's one explanation. Is it good enough for you? Yeah, we gave another one too, but that's good enough. Okay. All right, so did that buy everyone enough time to plug in negative 2 into the other component?
That's how it was.
Oh, we didn't order it? All right, whatever. Another thing for you, just for fun. Okay. Negative 8 plus 24 is positive 16?
Yeah.
Is that what you just said? Okay. And if you plug in 2, you get 4, here, I'll just trust you. 4i plus something, minus 16j. All right, whatever. Those are the positions at those 2 places. So at those places on the coordinate plane, when the particle passed through there, it had a horizontal component of velocity being 0. Okay, that's cool. And then let's do the same kind of thing for we're looking for now vertical components of velocity be 0. That is vertical tangents, if you like. I'm sorry, did we just say this wrong? I thought we were looking for horizontal tangents.
Well,
I just misread it again. You guys gotta catch me on.
Okay,
So you were right? Or whoever said it, right? I'm sorry. I thought. All right.
You don't have to read.
All right. Well, we're gonna switch the following. Sorry. I'm sorry. I thought this said horizontal tangents, and that's my fault. Do you understand the difference between those two things? Okay. The horizontal component is, of course, just dx dt. Yeah. So now we're gonna do that down here. Okay. My most sincere apologies. Next time I'll read better. I am a math teacher, though. Okay. What's dx dt? 6t. I mean, this is kind of somewhat. 6t equals 0. 6t. All right, so we get at t equals 0 and at t equals 1. All right, those are the actual answers to part B. All right, you're right. And if we plug in those values, that's nice and easy. Those are easy to plug in. I like zeros and ones. That's good. We get 0 I, 0 j, and -1, comma, -11. Okay. So then this is, so that's great. Good job. This is the horizontal and this is the vertical component, which correspond to horizontal tangent, right? So you understand this correspond, these two places at 0 and 1 correspond to vertical tangents, and these correspond to horizontal tangents. So this is all right. Okay. And then is the particle ever at rest? Could you justify that? What do you think? This is someone else to talk to besides Sue. He's on fire today. Yeah, Zoe, what do you think? And justify.
It's not ever at rest because the vertical and horizontal components are never equal to 0 for the same t.
Right, yeah. Is that clear with in everyone's mind? If that were to happen, and that could easily happen, if up here we got the answer like 0 and 2, and down here we got the answer 0 and 1, then at 0, the particle is at rest because both, it's settled in both the x and the y direction, right? Okay. So, no, and then say something like Zoe just said, okay? We need both components, dx dt and dy dt to be 0 in order for us to declare the particle at rest. Like we don't declare this particle at rest if it's a particle at rest if it's doing this.
But is that the same t value or the same?
Well, that's a bad example actually. What's that?
Is that the same t value? You're saying not the same coordinate?
Yeah, we need the t value to be, I mean, it should be true that if t is 0 here and t is 0 here, and we find that both dx dt and dy dt are 0, are 0, at the same t value, like say at t equals 7, then that also corresponds to a certain location, if that's what you're wondering, right? But there's no t value at which the time it's dx dt and dy dt are both 0. Okay, actually, this as far as the calculus goes, this is not bad. I just want to like make a commentary about physics as we do this. Yeah. Yes, actually, another great way to justify that. I think the way we just did, especially following on having just found out where dx dt and dy dt are 0, the best way to do it is the way we just described. But it also corresponds to when the speed is 0. But that's a little harder to like maybe to swallow, but right, because you have to like the speed is a complicated thing. But that is absolutely true. Yeah. That's a little harder to find. You could graph the speed function in like regular coordinates, and you know, yeah. Yeah, wonderful insight. All right, so go ahead and do this and this if you haven't already. Go ahead and beat us to it here. Find the velocity acceleration, and I'll just write these up. This is not the interesting. I want to make some commentary about it, but actually finding these things is not bad, right? Do you agree with my results? Nothing really startling about what we just did. Yeah, so we'll go to the next ones in a second here, but let me make just a commentary about what this picture is here. So this is a circle. Do you recognize that already, maybe, besides the fact that I have the picture here? Maybe you already forget that I showed you the picture. Do you know that this is a circle, right? Of radius 3, center at the origin. But also, it's keeping track of time motion. This is called uniform circular motion. I don't know if you've studied uniform circular motion, but it's a topic that you would encounter in the physics class. And so what do you know about uniform circular motion? Well, for any point like the one that we're talking about right now, when t is pi over 4, we have the position vector, looks like this in black. I'm going to highlight the velocity vector in red. We'd actually say what the position vector is. We should have, right? The position vector is positive 3 root 2 over 2 times I, plus positive 3 root 2 over 2 times j, isn't it? That's the black vector. Okay. The red vector, I'm going to put it up here just because it doesn't matter where we put the vector. Looks like that. Negative, positive, right? You can orient it right here at the origin too if you like. Okay. But I think it's helpful if we think of the particle as living right there. What does it mean for the particle to be here and have a velocity vector in that direction? Does that make sense to you, by the way? It should kind of like sit well with your intuition about what you know is happening. If we're swinging an object around in a circle, keys on the end of your chain, and then you let go right here, in what direction does it go? And the answer is it follows the red vector, doesn't it? If you were to let go suddenly, it would take off tangent to the circle. Beautiful. Okay, and then in what direction does this vector point the acceleration? Now I want you to feel like you're the keys and you're in there, right? Or you're on a ride or something like that. The acceleration vector points like that, doesn't it? Negative, negative are the two components. Does that sit well with your experience? Yeah? That your acceleration points inside to the inside of the circle? Yeah.
How would you like split that into a centripetal and tangential acceleration? I mean, this is kind of like a game.
Sure. I mean, so it's uniform circular motion. So there is no acceleration in the direction tangent to the circle. Okay, all of it is perpendicular to the tangent of motion, to the velocity vector, and that is always what happens with uniform circular motion. But we could make a comment about this, right? So this is like kind of the common argument that people may have had like when you're first in middle school, right? Like, oh, there's no such thing as centripetal versus centrifugal, right? Okay, we can have that conversation. Everyone's had that like conversation, right? I hope, right? With your like annoying friend or something, okay? We can be more clear than using words. We can like use math, right? So imagine you're experiencing this. There are two forces that you're kind of feeling being balanced, right? There's a force that pulls you into the center of the circle, right? And then there's a force that is acting. If you're stationary with respect to the circle, then there must be another force acting, and that's of course the force of the wall acting, or the force. To make sure I say it right. You are exerting a force on the wall of the thing that you're being flung around in, I guess, whatever, if you're going in a car around a circle or something like that. And then there's an equal and opposite force being acted out in the opposite direction, right? So there are two forces there in reality, right, is the point. I don't know what you want to, which one you want to call the real one, I don't know, whatever. But everybody's right is the point, okay. Anyway, one more plug for all you need in life is calculus. Okay. You don't need to go take physics, now, right? Okay. All you do, they'll tell you this, but it's just doesn't it just kind of fall out of the calculus? Just so happens that when you take these derivatives, you get this is what happens, right? It's just how it is. Sorry, I don't know. I don't know what else. What else can we say? Okay. All right. Back to more computations. So this is Emma's question, right? Find the direction of motion. Give me a unit vector in the direction of motion. So that's, we already computed the velocity vector. So we just want to let me say again what that was here, just for reference. Here, this is not the direction. It was negative 3 root 2 over 2, comma, positive 3 root 2 over 2, wasn't it? Okay. So just for reference. And then what is the magnitude of that vector? Does anyone know just by glancing at it? Should be easier than that. It's 3, right? It's if you simplify what you said, root 18, factor out the, right? Okay, root 9. Okay, you got it. It's just 3. Just to make it more obvious, we could write this way, right? Okay, and that almost just right there, we're done almost with the question, aren't we? What's the speed? Right? Speed is the magnitude of this vector. Is it? I mean, we didn't use the magnitude formula, but it's pretty clear to me that the magnitude of this vector inside here is 1, isn't it? Because those are values of cosine and sine that I know. They live on the unit circle. If you want to check, you can check that this is 1 unit long. Go for it, right? But that means the speed is 3, sorry, math class, unitless things, okay? 3 meters per second or whatever. And then the direction vector is the thing that's underlined over there, right? Yay for pizza. Sorry, no, we have to do math. Take it away. No, put it back there? Yeah, put them here. Yeah. Is that going to be enough? Let's see. Go for it. Thank you, guys.
Of course, thank you.
You guys are the best.
Thank someone's coming with plates. And
that would be helpful, yeah.
Of course. Yeah.
Sweet.
Yeah.
Thank you, guys.
Enjoy.
Thank you. Thank you. All right, we will in a minute. And then find the total distance traveled by the particle on 0 to pi over 4. Is that okay, by the way, for C? I just got interrupted to eat pizza. And then for D, yeah.
So for the direction, we didn't have to use that formula.
I mean, we did actually, right? But it's really simple here. So, do you agree with the speed is 3? You sure? We didn't use the formula there either.
Okay.
You might want to check, right? Dude, you go ahead and use the formula, right? Square root of this thing squared plus this thing squared, and verify that that does come out to 3. Okay, thank you, guys.
No problem, thank you.
Verify that it does come out to 3. Try it. Great. And then what is the formula for direction? Isn't it the velocity vector, which is this whole thing divided by 3, divided by the magnitude? So we actually did use the formula, we just didn't tell you. Okay. Find the total distance traveled by the particle. All right, so now you're integrating the velocity function, right? So from 0 to pi over 4. By the way, this one, see if you can do without a calculator, because it comes out really nicely, just because it's a circle. Okay. Square root of, it'll be negative 3 root, no, sorry. I need those functions, whatever they are. Negative 3 sine t squared. 3 cos. And do you see what I'm saying? Can you do this one by hand, maybe? Because the thing in here, I mean, stuff nicely reduces. But you can also hammer it into your calculator and you get the answer to this. Okay. Let me hand this stuff out, and then. actually don't think so. But yeah, we're going to I can't read much more from their desktop. We only really have two more major lessons. Let's see what we get through here. The thing I just passed to you is homework. This is just for fun. That's all I want to practice and keep you trouble. This is just for fun.
I actually want to wait till so you know what to look for. It's better to wait till we get to this.
All right, 36 minus 9, 2, 3, 4, 5, 6, 30 people, 6 pieces, 6 pizzas. So, 5 people on pizza. I think 2 pieces is safe, okay? And let's have ladies first, okay? So, ladies, please. There are 2 piles, maybe, so we can put them in different parts. Are they all, what are they? You can be the... Yeah, ladies first.
Go ahead.
You go. I was me this one. Me said these during history, like wait, stop talking. I need to write pages.
Okay.
Hang out. Oh, yeah, guys, sorry, I don't get pizza. Just kidding. Hang out for a minute.
Was it a girl's?
Are they all the same?
No, these are classes from
I can only eat cheese, so this
What else in your eye? I'm wrong. Okay, it just show up every day. Yeah, I always have. Oh, we have
Guys, you can come up then too and follow the ladies. I have enough. Leave some for
Yeah, Lois first. Sean wanted you announced ladies first. All we do is
Dude, that's an original joke, dude.
That's so funny, Eminem. Hey, Tigers.
What would you consider funny? Interesting.
Well, as far as
Higher class.
right, like, oh my god, dude, stuff every day.
Is just like do TOK.
It's so stupid.
It's like, hey guys,
GK's
what area of knowledge is this? Like, who is
excited.
Yeah.
I was like, okay, sometimes
What do you mean, son? TJ's always cool.
GK himself.
I don't like people.
What are you saying? Wait, are we out of place?
We're out of place again, Matthew.
Of course,
He just took a whole box.
So what do we do?
Take 2.
We're out of
Out of what? Plates? I have some. Yeah, you can. That's fine.
Is there any cheese left?
I thought you just took the whole thing.
I have. I know. They didn't have plates, man. Are those all empty? Thank you. Yeah. Thank you guys. Good job.
I think you're recording so long.
Ready to go.
I successfully.
I'm still recording. Yeah. That's good, man.